Here we go with question 3. This is practice exam 2 for response question number 3. All right, so we have a setup like this, and when I see something like this, I'm automatically thinking it's going to be something with energy. You got a spring and a block, you got a ramp with a curve, it's going to be a conservation of energy thing somewhere inside of here, probably. Maybe an oscillation, we'll see. So it says a group of students is asked to experimentally determine the spring constant K of a spring using a linear graph. No surprise, obviously, we know what this question's about. Students are provided with a block of known mass m. It can move on a horizontal track, negligible friction. The right end of the track is curved, and the end of the curved section of track is vertical. Okay, great. Shown in figure 1. In addition, they're only allowed to use a meter stick. Negligible friction, that's good. So that's what we get. We get a meter stick, and that's it. And we can measure the height over here, or how far we stretch the spring back, I'm assuming. Indicate quantities that could be measured by the students that would allow them to determine an experimental value of K using a linear graph. So this is going to be a conservation of energy thing. I'm always a little confused by these because I feel like I know what the answer is going to be, so I could tell you what these quantities are, but let's figure out how we're going to get there. So this is a conservation of energy problem. So we know we're going to have to do a spring potential energy, elastic potential energy, 1/2 kx squared. And that's going to turn into a gravitational potential energy over here. In the middle, there'll be kinetic energy, which at this point I don't care about because we can't measure the speed. We don't have a photo gauge or anything like that to measure the speed. So all I really care about is the spring energy and the GPE over here. So that's mgh. And we're trying to figure out K. So I'm going to rearrange these somehow to get K as like the slope of a linear function. So I might rearrange this to, I'm going to pull height. There's a bunch of ways you can do this. Equals. So I'm going to pull all this stuff over here. I'm going to say it's K. That's going to be my slope. And what do I have left? I have x squared and 2m in the bottom. Great. So then that's going to be my y equals mx. So the quantities that I can measure. So I know what I'm going to graph is h versus this big thing. But what I can measure, indicate quantities I can measure, and I could say measure the spring compression and the final height. Because those are things that can be measured with a meter stick. Briefly describe a method to reduce experimental uncertainty for the measured quantities. So you're going to want to say something like take multiple measurements at multiple spring compressions or something like that. So multiple spring compressions, compression distances, or something like that. And that way you have multiple measurements. You don't just have one measurement. I mean, if you're going to make a graph to find the slope, you're going to take multiple measurements anyway. So you could also repeat 3 times per distance, something like that. Okay. You're going to write much neater than I'm writing here on your AP test. Please don't scribble. Make it nice. Part B, indicate what quantities the students could graph on the horizontal and vertical axis to create a linear graph that could be used to determine experimental value of K. So I would say on the horizontal, I'm trying to squeeze this in over here. So on the horizontal graph over here, I would graph this x squared over 2m, x squared over 2m, and then the vertical, I would graph h. Once again, make this neater. Don't write, you're going to have more space, so I'm trying to squeeze this in, but you're going to have more space. Briefly describe how the graph can be analyzed to determine experimental value of K. Your answer may include an equation that relates K in the chosen feature of the graph. Well, I would say find the slope, how the graph can be analyzed. I don't know if they want you to write plot points, fit, align, find slope, and then slope equals K. So it's kind of funny that they say that, like, of course the slope is K, but you didn't necessarily have to set it up so the slope was K. So you could have said something like h equals K over 2m times x squared. And you would have just plotted h versus x squared, and then the slope would have been K over 2m. So that to find K, you would have had the slope times twice the mass. So that's why they needed this over here. But for us, the way that I did it, the slope was just K. Okay, and then actually they're not having you plot the points for this one. So this information applies to parts C and D. In a later experiment, so basically forget everything that just happened, that's what that means. Oh, hold on, we can't see that. There we go. In a later experiment, the students are asked to determine an experimental value for the mass mg of a glider. The glider has length L equals, so that's the width of the glider, is initially at rest, okay, on a horizontal air track, which allows the glider to move, get this over here, along the track with negligible friction. Great. A string is attached between the glider and the spring with the spring constant. They tell you the spring constant as shown in figure 2. Okay, cool. The glider is pulled to displace the spring an amount x, so you pull this over and from equilibrium and then released. The glider reaches its maximum speed before passing through the photo gate. Okay, so that's the glider is going to be going. It's going to go to constant speed through the photo gate. That's awesome. The constant speeds are nice. The photo gate measures the time the glider takes to pass through it. So right away, we're thinking about some sort of velocity of the thing, and it's going to be the distance over time for the photo gate, L over T or something like that, because we're measuring the time. So I'm just kind of keeping this in the back of my head that velocity is the length of the photo gate divided by the time it takes to go through it. Table 1 shows the students' measurements of the spring displacement from equilibrium and the time taken for the glider to pass through the photo gate. Cool. Alrighty, part C. Okay, that was just all background information. Part C. Label the axes of the grid provided with measured or calculated quantities. Include the units as appropriate. The graph quantities should yield a linear graph used to determine the mass mg. So we've got to figure out a way to get the mass out of this whole thing. So this is going to be a conservation of energy thing again. And this time, where did it go? This time we are doing basically spring energy here is kinetic energy there. So this is going to be a 1/2 kx squared, and this is going to be a 1/2 mv squared over here, right? So let's do all that in like this space right here. So I'm going to just start off with 1/2 kx squared equals 1/2 mv squared. And we already figured out that this v is L over t. The halves can go away. So let's do kx squared equals m times L over t squared. M is the thing that we're trying to find, so we want that to be the slope of something. So I'm just going to pull this k to the other side and square those things. So I'm going to have x squared equals m times L squared over k t squared. Okay, it's not pretty, but I guess it'll work. So I'm going to have this on my y-axis, this is my slope, and then this is on my x-axis. This whole thing on my x-axis, which I'm not that excited about doing because, I mean, we have L. Let's just remind ourselves. L from the problem, it's back on the other page, is 0.15. And then K we have as a number as well. K is 25. And so, you know, we just square L and divide it by K, and then we're really graphing 1 over t squared, but I'm going to keep this inside of here. And once again, you could actually rewrite this. You could write it as x squared equals m L squared over K times 1 over t squared, in which case this whole thing would be your slope. But I don't know. It's probably better to do it this way, because the way I'm doing it, I'm going to have to do this calculation 1, 2, 3, 4, 5 times. And if you do it this way, you only have to do this calculation. Well, I still have to do 1 over t squared, but anyways, you only have to deal with this part of it once. Whatever works for you is totally fine. So then here is the grid. Of course, we knew that this was going to be here. So we are supposed to label the vertical and horizontal axes, label the axes of the grid with measured or calculated quantities. So on my y-axis, I'm going to have x squared, and on my x-axis, I'm going to have L squared over kt squared. There it is right there. Okay, so then on the grid provided, create a graph of the quantities indicated in part C1. So clearly label the vertical and horizontal axes, plot the corresponding points, and then we have some room for scratch work. So I'm not going to do that because that's just going to take up a bunch of time, but you know how it's going to go. So I'm going to have another section over here, and this is going to be x squared that I'm going to calculate. And then I'm going to have another section over here that's going to be L squared over K times 1 over T squared. And I'll just calculate L squared over K and then multiply that times 1 over T squared. And I'll have all those quantities, and then I'm going to need to figure out a good scale over here. Remember, the AP people are going to want to see you use a good chunk of this graph. So the values here are going to be going from, well, they're going to be pretty small. So I'd probably start from, start from 0 is always a good place to start. And then you're going to be going up, and you pick a value for here that's going to be appropriate, and then pick a value for over here that's going to be appropriate. And then they're going to want you to plot points. So your points are going to be like this. Hopefully they're going to be pretty linear. And then you want to take your straight edge or another pencil or something. They really want you to draw a nice best fit line as best you can that goes through. I mean, they're not going to grade you if your line's a little messy, but yeah, okay, that's pretty good. And then remember, when you're finding the slope, they don't want you to use one of your plotted points as a slope. You got to find a point on your line right here, like this point right here. And be careful about like drawing another dot right there, because they're going to think that that's a point that you plotted. So when you're finding the slope and you're doing your change in y over change in x, you're going to want to pick a point that's on the line that you drew. So I don't know, maybe I'll pick this point right here and I'll do whatever that is, and then pick another point right here and do whatever that is. So it's a little bit of a pain. I feel like it's not really an appropriate use of time, but I'm not the people who design the test, so that's that. So there we go, draw a best fit line and then calculate the experimental value for mg. So I'm not going to go through that whole business because I feel like that's pretty easy for you all to figure out. Okay, that is the end of that question. And then of course the next one we will get to question 4.